Looking at section 1.3, day 2. So chapter 1, section 3, day 2. Let's start with this problem number 5 in our notes and go through how to simplify these trig functions. And if you tried to plug in pi over 2, I would get 5 of cosine pi over 2 divided by 2 cotan pi over 2. And we all know that this is going to head, this is 0. It's not heading to 0. And this is also 0. So I get 5 times 0, 2 times 0, so I get the 0 over 0 indeterminate form, which, you know, is a bummer, but in the same sense, it does tell me I should be able to do something with this problem. So I'm going to try and work a little bit of trig techniques on this, and let's just see if we can simplify it a little bit more. Well, this 5 halves is really a multiplier, and there's a property that says you can bring the scalar out front. So let's do that. It'll just help this look a little bit simpler. And we'll have the limit as x approaches pi over 2. Cosine of x, pretty simple. Cotan is defined as cosine x divided by sine of x. And from here you can see, well, I could cancel my cosine. Cosine over cosine could cancel. And then I'm left with 1 over sine here, and that will flip up and look like 5 halves the limit as x approaches pi over 2, and this will just turn out to be sine x. Because remember, when you divide by a fraction, it is like multiplying by its reciprocal. So that's where I'm seeing the sign come up to the top. And now let's plug in our pi over 2. And I'll have 5 halves times the sine of pi over 2, just by substitution to analyze this limit. And sine of pi over 2 is 1, so we get 5 halves times 1, answer 5 halves. Problem B. Problem B, we are headed to pi, and if we try to plug in pi, if we plug in pi, we'll have x, or pi, excuse me, we'd have pi times sine of 2 pi divided by sine of pi. Well, this would be 0 and this would be 0, so we get 0 over 0, which let's try to do some trig work, maybe some simplifying on this. If you recall, and if you look up on that trig reference sheet, you would find that we could define the sine of 2x as 2 sine x cosine x. It was a trig identity that you had picked up last year in pre-calc. So a good one to keep in your mind, and let's work with that then. So we'd have x, and instead of sine 2x, let's put in 2 sine x cosine x, just the substitution there, all over sine x, and then you can see we can cancel sine x over sine x. And now let's try substituting in our value of pi. So let x go to pi, and we'll have pi times 2 cosine pi. The cosine of pi is -1. And it appears that our answer is going to be -2 pi. Problem number 6. Let's just try substitution, see where it takes us. Always the first approach. So if I put in 0, I get the cosine of 3 times 0, or 0. And then I'd have over 0, which we can see would be a problem. Cosine of 0 is 1, so I end up with 0 over 0. And there's no algebraic technique I can see to get rid of 0 over 0, nor is there a trig identity that I could substitute in. So on this one, I don't believe we can get around it. And so we're going to, let's try looking at its graph and see if we can determine the limit. So as we approach 0, so from the left as I approach 0, it appears that my function is headed to y value of 0. And as I let my x value come into 0, it too has a y value of 0. So I think we can clearly answer that 0 is the limit. Let's look at evaluating one-sided limits. We're going to either analyze from the left side or the right side to help us, well, probably from both sides, to help us analyze what the overall limit is at the x value. So on this one, we are looking at an absolute value function, and notice that we've got the same expression on top as we do in the denominator. And if I ignored my absolute value signs, I would say, well, those would cancel, wouldn't they? And I'd get a value of 1. That would be true if x were positive, but if x were negative, we would have, I'm just trying to circle those, not put zeros, but we would have some differences then with the signs, and that is what produces the graph that looks like this. Notice we're coming in at -1 for a height here and +1 for a height here. And I want to look as x approaches 4. Well, as x approaches 4, 1, 2, 3, 4, we can see we have this jump discontinuity. And so by looking at the graph, I could say, well, this does not exist. Let's look at it from an algebraic point of view. So breaking this limit down into one-sided limits, let's look at 4 from the right first, perhaps. And here's our expression or our function. And if I look at it 4 from the right, I can actually take values and plug in. Let's let x get close to 4 from the right side. So I'm going to put in 4.1 because that's just, slightly bigger than 4. On the top, I have the absolute value. I'm going to get 0.1 absolute valued over 0.1 on the bottom. Absolute value of 0.1 on top would be 0.1 divided by 0.1. We can see that equals 1. And that, checks out with the graph that we had 1 for our answer. Now let's look at it approaching from the underside of 4, from the left side of 4. So still we've got the same function, the absolute value over x minus 4 equals. Now let's take something slightly smaller than 4. I'm going to suggest 3.9. Absolute value at the top, 3.9 because it's slightly smaller than 4, coming in from the left side of 4. On top, I'm going to have the absolute value of -0.1. And on the bottom, I'm going to have -0.1. On top, if I absolute value that, this is where the top flips to a positive, but the bottom maintains its negative position, and I get -1 as my answer, and we can see the graph coming down below. When things are smaller than 4, it's going to be a negative answer. So the overall question is, does the left agree with the right? And we'd have to answer no to this question, and therefore this limit does not exist. So that's one way to analyze absolute value ones. If you have trouble with them, is just plug in some numbers. Part B, this is a piecewise one, and for piecewise ones, it's often good to look at it from the left and right side of a critical value, and the value we wanted to look at here was as x approaches 1. And I'll notice here that the piecewise function breaks off at 1. It's kind of like handing off from a quadratic function to a linear function, all occurring at the spot x equals 1. Now, let's analyze it from a left and right limit perspective. So from the right side of 1, if I were slightly bigger than 1, say 1.01, I would fall into this bottom category. So my function is going to be 3x that I follow to find its limit. And when I'm slightly bigger than 1, you could put something bigger than 1. I'm going to go ahead and just plug 1 in and see what is happening exactly at 1. And it would be, the answer would be 3. Let's look at the limit coming from the underside of 1, a little bit smaller than 1. And for that one, which piecewise rule must I follow? Well, this one suggests that when x is less than 1 or equal to 1, we follow this top rule. So here's going to be my function for it. Let's plug 1 in. We're going to have 4 minus 1 squared which turns out to be 3. And this is interesting. The left side does agree with the right side. The left does equal right. And that's a nice thing because it allows us to conclude then the limit as x approaches 1 of our piecewise function f of x is indeed 3. The squeeze theorem. The squeeze theorem allows us to analyze functions that we maybe would not be able to otherwise. So the idea is we're going to be able to squeeze the function we're interested in between two other functions. And look at how this is organized here. It's saying that the function h is smaller than or equal to the function f, which is smaller than or equal to the function g. So we have an orderliness about the functions here. One is definitely smaller than or equal to the middle one, and the one to the right is definitely greater than or equal to the one in the middle, f of x. And that happens for all x's in the open interval containing c, except possibly at c itself. So if we can find the limit of the function that is below what we're interested in, and we can find the limit of the function above the one we're interested in, because this is the one we're interested in, I'm trying to put eyes there, then that limit is going to be the limit forced upon our function f that sits in the middle. The graph is probably the easiest way to see these. So here's my top function, my greater function. Here's my bottom function, always less than or equal to my function f, which is the middle function, the one I'm interested in. And so by the squeeze theorem, I can predict what g function does, and I can predict what h function does, and I can also identify what their limits are. That's going to force, since I know that f sits between these two functions, it squeezes in the function to be L as well for f. And that premise, or that idea, is used to help prove two very special trigonometric functions. And these are ones that you will have to memorize for the AP exam. They are expected that you would know them. The limit as x approaches 0 of sine x over x is 1. And the limit as x approaches 0 for 1 minus cosine over x is equal to 0. On this very first one, the sine x over x can also be reversed and written as x over sine x, and it too has a limit of 1. So no problem on that. Number 2, I cannot reverse. That one does not allow you to invert the fraction. So utilizing these two special trig limits, let's look at a few problems. So letter A, the limit as x approaches 0 of sine of 7x over 7x. Well, you may not think that these two look much alike, but indeed they do. I could do a little technique and just say, let u equal 7x. And then I could come in here and say, well, you know what then? This limit as x approaches 0 of sine u over u, because I'm replacing 7x with u, now takes on a close similarity to sine x over x. And the answer to this one is 1. So I guess the idea behind this is when you see the sine of something like 7x over the same expression 7x, you know your limit's going to be 1. And the way you can prove it is use just a little substitution technique. Now letter B, a little different, isn't it? I have 5x, but here I don't see 5x. I only have x. So I can't quite do that same trick. However, I would love for these to look alike, right? They must look alike in order for me to use this theorem. I can do a little trick here. So let's go the limit as x goes to 0 of sine of 5x. And I need to create a 5x on the bottom. So here was our x. Well, the easiest way to do that is to multiply by a 5, right? A 5 on top over a 5 on bottom causes no harm. That's like multiplying by 1. So now I'm going to undo my parentheses. Didn't quite want to undo it all, but I had this 5 here, right? let's bring that one in and take this one out front since it's a scalar multiplier type one. And now, kind of looks like a little magic, doesn't it? We have sine 5x over 5x. That will give us an answer of this 5 that's outside, and the limit, this evaluates to 1, so I get 5 as my answer. Maybe replay that if it looked a little difficult. Part C, we've got 2 sine of 5 theta, Greek symbol theta, over 3 theta. So the easiest thing is let's clear these out. Let's bring those scalar multipliers out. So we've got 2/3 coming out front. I'm just trying to make this look a little bit cleaner. So I've got theta going to 0 of sine 5 theta. Now, could I bring 5 out? No, because it is inside the sine function. So that must stay there. Well, like we did last time, we said, you know what? If we have 5 theta here, we need 5 theta there. But in order to do that, I'm going to have to multiply by 5 over 5 because 5 over 5 is like multiplying by 1. Okay, now here's where we get, very magician-y. We're going to bring the 5 from here out front, and I'll have 5 times 2 then, and then this is sitting golden because it matches up. So I'm going to have 10/3 times 1, giving me the answer of 10/3, because the limit of this is headed to 1. Some tricky stuff, huh? All right, letter D. Maybe we'll make this our last one. First thing that catches my eye is I got a 4 and a 4. So I think I'll do some factoring here, pull that GCF, and I've got 1 minus cosine of x over x. Now this 4 is a multiplier, so let's swing it out front. So we're left with 4. The limit as x approaches 0 of 1 minus cosine x over x. Now look back on your theorems and you will notice that this is one of the basic ones that we should know. The limit as x approaches 0 of 1 minus cosine x over x goes to 0, and that's going to give me 4 times 0. I get 0 as my answer. So we'll have just a couple things to clean up when we get into class. We'll do E and problem 83 and homework tomorrow.